So, what is a string?
Array of characters.
Yeah, it's a sequence of characters, right? So, string algorithms are very, very important. We're going to look at a couple of important algorithms. Well, actually, three. We're going to look at three different string algorithms. So the first thing we're going to look at an algorithm called the longest common sequence, which we're going to abbreviate to LCS. And what we're going to do is we're going to take one string, whatever it is, a sequence of characters, and then we're going to look at another string. And what we're interested in finding is the non-unique string, which can be taken as a string from the sequence of the same character. So if you see over here, if we look at A, it matches, and as we go forward by 1, we get a D, forward by 2, we get another D, we got a D here, so it's AD. Then eventually, if we go forward 3 more, we get a B, and 2 here, we get a B, so that's another match. 1 forward, we have a C, both of them, and then this one forward, we get a B. Now we're out of character, so we have 1, 2, 3, 4, 5. So that's the longest common sequence. Now, the longest common sequence may or may not be unique. You may have more than one sequence. For example, maybe this B can be matched up over here as the fifth, and maybe somehow you can go backwards and end up having a different sequence of characters. So, but what's unique is the length of the longest common sequence. So what is the length of the longest common sequence? And of course, we should be able to actually get the length of the actual sequence, which, by the way, I'm going to leave for a homework problem for you guys. So we'll talk about that a little bit for next time. Okay, so what we have here is we're going to define x and y. We're going to say they are strings. So they are non-empty sequences of characters with a length of at least one character. Epsilon is going to be the empty string, which will be a string with no characters. It will be a string of length 0. Okay, then we'll define P and Q as single characters. So characters make up strings. Some strings only have one character, but strings can have 0 characters, 1 characters, or many characters. So P and Q specifically will be 2 characters which are not equal to each other. So again, if you want to choose, you can choose, for example, C could be X, and B could be Y, because they're different. Or X could be A, and Y could be B, as long as they're different. You cannot have X be A, and then you cannot have, for example, Y to be, or the Y to be A also. Not Y, sorry, P and Q. P and Q. So talk about individual characters, P and Q. So they have to be different from each other. So if A is P, then Q can be B or D or E or C. Okay? It doesn't matter which one. So we'll define the LCS, or the longest common sequence, recursively. We'll define it recursively like this. We're going to say that the longest common sequence between the string X, which is a non-empty string, and epsilon is epsilon. Imagine this string, for example, being nothing, no characters at all, epsilon. So therefore the longest common sequence between these two would be nothing, because you have nothing to choose from the second string. Right? Okay. So likewise, the LCS of epsilon and y is also epsilon. It's the empty string. Now, if we have the LCS of px and py, let's make sure we understand what px and py are. Px and py. P is a single character, where x is a string. Therefore, P is a single character followed by the string x. So Px essentially is another string. It's the character P followed by the sequence of characters that makes up x. In other words, Px is the string that starts with the character P. Not the character P, but some character, which we'll call P. We don't know what it is exactly. So Px is a string. What's the length of Px? It's one more than the length of x. Okay. So therefore, we're going to consider Px and Py. Of course, we understand that we don't know about x and y, but we know that P and P are the same. So therefore, the longest common sequence of Px and Py will start with P because it's an immediate match, followed by the longest common sequence of the remainder of Px and Py, which is x and y. Does that make sense? Okay, so the longest common sequence of Px, Py will be P. Again, P is a character. It doesn't have to be a character. You can think of it as a character, or you can think of it as a variable that's holding a character, such that P and Q are always different. So it will be P followed by whatever is the longest common sequence of the remainder of the strings. So in a sense, we've consumed a single character of the first string, Px, which is P, and a single character of the second string, Py, which is also P. And so therefore our complexity, if you look at the length of Px, what's the length of Px? I don't know. We'll call it M. What's the length of Py? I don't know. Let's call it N. So we have M and N. So therefore, in terms of complexity, we've taken one character here, so therefore the complexity is going to be equal to whatever work we did to get that single character match, plus the recursive complexity of LCS of n minus 1, m minus 1. Does that make sense?
So this is LC, PX, and PY. If I change it to LCS, PX, YP?
YP, that's a different story.
Oh,
Then we don't know. Absolutely, yeah. So the question, what's your name again?
Yuha.
Yuha.
Yes.
Yuha.
Yes.
All right. So I'll say it 5 times today and never forget again. Also, it turns out that he's in 2 of my classes. I just thought it was his identical brother. All right. So Yuha said basically Px, Py, he understands this part. What if it was Px and Yp,
yes.
which of course could be. That would be the string Y followed by the single character of P or whatever we want it to be. Then we wouldn't know exactly what it is. We wouldn't know if we would match in the first character or not. So it's a different story. Of course, we're going to be able to solve the problem. So again, in terms of complexity, I don't know how long Px is, I'm going to say N. I don't know how long Py is, I'm going to say M, like Mary. So therefore, we are looking at the complexity, or T of NM. And in this case, we could say it's equal to 1 plus T of N minus 1, M minus 1. Because each of the strings now has one less character. Right. Now, in the case of Px and Qy, because P and Q are different strings, they're not going to match. Which means when you compare the first character of this string to the first character of this string, they will be different. The first characters don't match, but it doesn't mean that this P, okay, so doesn't mean that this P is not going to match to the Q, right? But if I remove, for example, the Q, it's possible that P will match the first character of what? Right? Maybe yes, maybe not. At the same time, P and Q don't match, but if I remove the P, it's possible that the first character of X matches Q. Maybe yes, maybe no. In terms of complexity, we are looking always at the complexity of Mn, or Nm, whatever we want to choose, okay? And so in this case, we're consuming one character for both of them, but in this case, we're only consuming one character from one of the strings. Either take the first one here and next one here, so therefore the T of Nm is going to equal to T of N minus 1m plus T of N minus 1. Does that make sense? Because I'm only reducing one of the strings by a length of 1. Somebody had a question? Yes?
Why we are placing P or Q in front or back of a string? Why we are not comparing directly the strings? Why we are considering separate characters?
We're just looking at scenarios. So basically, we're trying to find out in general what's going to happen. Because if I just use X and Y, then we'd have no idea what's in X and Y at all. So when we choose P and Q as being the first characters of the string, or P and P, or Q and Q, or Q and P and Q, then we can see what's going to happen in reality. In reality, when you compare the first character of x to the first character of y, it will be just the same as PP, QQ, PQ, or QP. So we're just seeing the scenarios as they're going to play out.
Okay.
Normally, we will treat the string as a whole, but for analysis purposes, we are removing the first character so we can see how the complexity is going to decrease each recurrence. Okay? All right. Oh, I'm sorry, this is so small. These are called microscopic notes. Very, very small notes. I can make them bigger. Oh yes, I can make them bigger. But it's a lot of work. I have to push a lot of buttons. Very complicated. Okay, so we talked about the string length. Everything okay, Scott?
Yeah, sorry about that.
Right, still internship stuff going on?
Yeah.
That's what I figured, okay.
Sorry.
VIP stuff. Okay, so when I say, so this is basically the symbol we're going to use for the length of x. So the length of x is the length of the string x is going to be n. The length of the string y is going to be m. W will be the worst case analysis. Worst case analysis. Worst case analysis of 1 and m is going to be m. Why? That's the worst case. Okay, maybe somebody can explain to me what the heck that's talking about. What is 1 and what is m? Somebody. Louder.
First one and last one.
What does 1 correspond to?
Only one common sequence.
What does 1 correspond to?
Only one character matches the string.
No.
Length of the first string, position.
Ronaldo?
Length of the first string.
Yes. Okay, so this one means that the length of the first string is 1. And the length of the second string is m. What is it? M. I don't know. It's some value of m. We can assume 1 or higher or whatever. It could be a million. I don't know. So why would W1m be equal to m?
So whatever.
Number of comparisons
Yeah.
will be n.
In the worst case. So we are comparing this one character to the first character of the second string, and it's not matching. And the second one, and it's not matching. And the third one, it's not matching. Tick, 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 to the mth one, and it's matching or not matching. If it matches, we did m comparisons, and we got a match. If it doesn't match, we did m comparisons also, and it didn't match. So the worst case for determining what is the length, the LCS, in this case is going to be m. Exactly the same thing, except now the second string only has 1. So now the recurrence.
So, Professor, can you please come again? Length of the string you are saying? Common sequence would be.
This is the length of the string,
Yes.
x. This is the length of the string, y.
Yeah, LCF would be 1 in any case. You know, whatever you are comparing only one character.
The length of the string will be, the length of the string, the
LCS would be
the most is 1, the least is 0, but the amount of work.
It's m.
I'm just looking at the worst case analysis. Same thing here, right? Okay, now, so now what we're going to look at is we're going to say the worst case of nn. So now we're going to let n and m get bigger. And the reason, why do we need this? Why is that important? Well, it's important because these are, in a sense, the base cases. Because as we keep consuming characters and getting shorter and shorter characters after going through, because we're moving 2 indexes through 2 strings, the strings are getting shorter. Eventually, one string will be down to 1 character. The other string will have 1 or more characters. Therefore, we're going to go to this basis. So we'll be able to solve it. So in this case, the worst case of nm, we're saying is going to equal to w of n minus 1 plus w of n minus 1 m. Does everybody understand what that might mean? Or who understands what that means? Scott? What do you think?
So the worst
So
case
what happens in this scenario?
The length of one string is n.
This second string is getting shorter,
Yeah.
we've excluded that string. So we're considering now, we're looking at finding the LCS of the string, the first string, minus its first character against the entire string. Because what happened? The two first characters
We're not.
didn't match. So we're going to remove the first character of the second string and try to match the second string starting at its second character to the entirety of the first string. And that might give us the LCS. But on the other hand, it might not, because by stripping off the first character of the second string, that first character might be part of the LCS. And by stripping it off, you're not going to find the LCS. Just because the two characters didn't match. If you throw this one away and go here, what happens if this character could have matched here? And that could have been led to the LCS that was the longest. So we can't exclude that character. We can exclude the fact that the first two don't match. They don't match. But it doesn't mean we can throw away this character completely. So that's why we have to add the work of keeping that character in the second string, but removing the first character of the first string. And that's why the work is going to be WNM, in the worst case, is going to remove one from the right string, using the whole left string, plus remove one from the left string, using the whole right string. So we know that that's a recurrence. That's a worst case recurrence. And since n(m-1) is a higher complexity than n-1, m-1, and n-1m is also a higher complexity than n-1, m-1, we're going to say if we simply reduce this to n-1 and this to m-1, then they become the same thing. And therefore we can add them, we have two of them, but in this case, since we've reduced them, what we had originally is bigger than this reduction. So WNM is greater than or equal to 2W n-1 m-1. Does that make sense? Did we get through this? Okay. Tiny. All right, this is still, I don't know why I made it so small. But I can't, okay. All right.
So here in N and M, we are assuming that the first characters are P or Q in both the strings.
Now it doesn't matter. The P and Q are just demonstrating that you are considering the first characters. That's all.
So why we are reducing one in N or M there? If we are
If I didn't use P and Q, I would have had to use like X sub 0 and Y sub 0. And I don't want to get into indexing.
I'm asking that why we are reducing one in M or N. If we are not considering the P or Q in the first place.
Well, hold on a second, hold on. Okay, now I have to go again very, very small. Backward. And very, very large. Too large? Okay, so what we're saying here,
Yeah, why we are
okay,
doing
what we're
N-
saying here is this is equivalent to P and Q not matching and removing Q from Y. This is equivalent to P and Q not matching and removing P from X. So when we say, so the length of the string PX from the original slide will be N. But now we're just calling it X because we don't need the P anymore. But of course P just represents the first character. So therefore, if you are reducing the second string length by 1, that means you are eliminating the first character of the Y string, which we used to call Q, but we really don't know what it is. But all we're saying is, in the worst case, the first two characters don't match, so keep the whole string and shorten the second string by removing its first character. But don't get rid of this character, because this character may be useful for the LCS in case it's used in mixing up with the first string with the P removed.
So Professor, if we are not considering P or Q in X or Y now. So why we are reducing?
I'm just saying that P and Q are implicitly there. We're no longer singling them out. The idea, this means that the first character of Y has been removed, We used to call it Q, now we're just saying it's just going to be Y with the first character removed, whatever that was. And the reason we're removing it here and not removing it here is because the first characters of the string did not match. See, if you have the same strings and they match all the time, you'll just get match, 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 match. Maybe they're the same length. Therefore, that cost of the LCS will be linear, and you'll just get the same string. But we don't know how that's going to work. That's not necessarily how it's going to work. Okay? So if we look at the first characters, they don't match. Then we'll take the whole string here, and we'll take this character out, and we'll reduce this by 1. Because the LCS is going to be here. Or possibly take this whole thing and reduce this one by 1. Because if they don't match, then one of those two is going to lead to the LCS. Maybe both, because it's not unique. Not guaranteed to be unique. Okay? So the P and the Q are sort of implied. They're in there, but we don't talk about them anymore. Okay. All right, enlarging. Too big. All right, so now W and M is greater than or equal to 2W and M minus. Okay, repeating I times, we have W of N and M, so this is repeated substitution. If we repeat this I times, we're going to get 2 times 2 times 2 times 2 times 2 times W of N minus I, M minus I, because each of them is being reduced I times, which is going to equal to 2 to the I times W of N minus I, M minus I. Suppose N is less than N. Now they could be the same, or they could be different. Now, letting N less than M, it's just as good as letting M less than M. N. It doesn't make any difference which one. We're just saying one is shorter, one is longer. Which means that as we keep reducing them, one of them will go to unity first. When they go to unity, the W of 1, whatever, constant, is going to equal to that single value. That's the base case that we set up earlier on. So, suppose N is less than N, then we'll let I equal N minus 1. So now we're going to have 2 to the N minus 1 times W of 1 M minus N plus 1 is going to equal to M minus N plus 1 times 2 to the N. So our analysis leads to the following result. And the result is the complexity is exponential in the min of N to the M. It's exponential in the smaller of the two variables. Does that make sense? Because that's our result here. Everybody understand? M is bigger, so we'll take M minus N plus 1. That's going to be what? The remaining characters in M. I suppose you can. I wonder if you can just write N times 2N. But anyway, it's going to be 2. This is the exponential one times 2 to the power of the shorter string. Exponential. So it's an exponential complexity, which seems very, very high. So the purpose of this lecture is that we're going to actually find an algorithm to find the LCS, which is actually not exponential at all. And we're going to look at a class of algorithms, which are very, very important, and they're called table-driven algorithms. Table-driven algorithms. Table-driven algorithms. Also known as dynamic algorithms. Dynamic algorithms, table-driven algorithms, it's the same thing. We create a table, we solve the table. So, let me talk a little bit about table-driven algorithms. How many people remember the Fibonacci sequence? Remember the Fibonacci sequence? Okay, so the Fibonacci sequence, which we did earlier on, we have T of n is equal to what? What is the nth Fibonacci number equal to? Louder. Yes, okay. So the nth Fibonacci number is equal to the n minus first Fibonacci number plus the n minus second Fibonacci number. So basically the nth Fibonacci number is the sum of the two previous Fibonacci numbers. And of course, in order to make this recurrence dependent on two previous numbers, we need to prime or start the initial values of the Fibonacci sequence, which we start at what? 0 and 1. Let me show you something. So let me show you how this is going to work. Oh, we have some nice stuff to erase. I'm ready. Okay. So let me know if this pen looks okay. So, can you see it? The nth Fibonacci is equal to f of n minus 1 plus f of n minus 2, such that the Fibonacci 0 is equal to 0, right? And the Fibonacci 1 is equal to 1. So, we can write a recursive function for that, right? Because basically, we see that there's a recurrence. So f of n is equal to this plus this, right? So we would write the recursive function like this. So Fibonacci of n. What's the first condition we're going to check? If n is equal to 0, or n is equal to 1, what does that mean? Then I'm looking for the 0 or first Fibonacci number. I can just return what? I can return n, right? Else I'm going to return what? I'm going to return f n minus 1 plus f of n minus 2. Okay. Good? Again, the precondition is that n is a what? Non-negative integer. Precondition. If you can't guarantee the precondition, you got no postcondition. All right, you got no postcondition, so you got to have a precondition. Okay. So now we can analyze this algorithm, and so the algorithm is going to be analyzed like this. So t of n recurrence. T of n. Let's look at the recurrence only. Is going to equal to what? T of n minus 1 plus t of n minus 2. We're going to have to add those two recurrences together, right? We're going to have to add those together. Now, we're going to do repeated substitution, right? So what is the value of t of n minus 1? T of n minus 1 is equal to t of n minus 2 plus t of n minus 3, right? We can do the same thing here, keep substituting it, and then try to get the solution. It's going to take a long time.
Yeah.
What do you think is going to be the complexity of Fibonacci? Which, by the way, Fibonacci is very, very similar to the algorithm we're looking at, and I'll tell you in a second why. What is the complexity of Fibonacci like this?
Yeah.
Can't hear what you're saying.
Yen.
I don't understand a word you're saying.
Yen.
Yen? N! You're saying yen. I thought you were saying what the Japanese currency was. It's a yen.
Yeah.
Okay, so the complexity of this is going to be, it's going to be exponential. And I'll show you why it's going to be exponential. Because, so n comes in, right? We're going to do a recurrence tree. So n comes in, and then what happens? So we need the Fibonacci of n. But the Fibonacci of n is equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2, so we get to evaluate both of them. Let's look at a specific value. Let's say I'm looking at the 6th Fibonacci number. So 6 comes in, right? Which means I want the Fibonacci of 6. So what I'm going to do is I'm going to recurse with the Fibonacci of
5.
5. And when it comes back, I'm going to add to it to the recursion of the Fibonacci of 4. But when I come to the Fibonacci of 5, that's going to be evaluated by the Fibonacci of 4, Fibonacci of 3. This is going to be 3 and 2. This is going to be 2 and 1. That's a base case. This is going to be 1 and 0. This is going to be 1 and 0. This is going to be 2 and 1, base case. This is going to be 1 and 0. When I come back up here, it says, okay, now I got this value, plus the Fibonacci of 4. It's going to say, that's equal to the Fibonacci of 3, plus 2. 3 is going to be 2 and 1. 1, 0.
1, 0.
1 and 0. Now, why is this exponential? Well, would you agree that I'm evaluating the Fibonacci of 6? That's my really primary task? That's my primary task. So any number that comes up at any node is the evaluation of that Fibonacci number. I'm evaluating for the 6th Fibonacci number. So I'm now evaluating for what? The 5th Fibonacci number. And now I'm evaluating for what? But then I'm doing it again here. I already know what it is. And then I'm evaluating for 3, and for 3, and for 3. I'm doing 3 times. How many times am I doing 2? 1, 2, 3, 4, 5. I'm doing a lot of repeated work, which I could save if I just kept a table. A table-driven algorithm for Fibonacci can be much more efficient. And actually, let's just see the amount of work we're doing here. So if we look over here, basically all of these are going to be, you count these as the number of recursions you're making. Okay? The zeros and ones don't count, I suppose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can say that T of 6 is equal to 12. Now, how can we show that it's how can we show that it's exponential? Well, because if we went for 7, T of 7 would equal to 12 plus whatever is 5. 1, 2, 3, 4, 5, 6, 7 plus 7, which is equal to 19. And then if I did T of 8, that would be equal to 19 plus the T of 6, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's basically an exponential function. It's an exponential function. But we can write it into a table-driven function by the following approach. So
How
we
can
have a
we
table.
write T of n? How can we write T of n?
You know, I like your thinking. We have to think about that one. It's actually a good thing that Fibonacci has a closed form. Did you know that Fibonacci has a closed form? Fibonacci actually has a closed form, which I've known for most of my life. Well, my older brother, who was a nuclear physicist, who didn't know that, who came across that in a math book, and he goes, "Did you know that Fibonacci has a closed form?" I said, "Yeah." He goes, "How can that be?" Even a PhD from Yale in nuclear physics didn't prepare him for the amazingness of the Fibonacci having a closed form. A closed form! You just plug it into a formula and you get the Fibonacci. So cool. And it's got a radical 5 in it. He goes, "There's no way it's true." It's true. So closed form Fibonacci has a radical 5 in the formula, a bunch of radical 5s. And it always comes out as an integer. Okay. Next point. So I'm not going to worry about this. I don't know right now offhand how to do it. I have to think about it. But it does have a closed form, which is even more impressive. Which means, if it has a closed form, what is the complexity of the closed form? Yes, theta 1. Because closed form, it means a formula. You plug in a certain number of operations regardless of the size of the n. All right, but we're not looking at the closed form. Let's take a look at the dynamic approach. So the dynamic approach can be something like this. So let's think about it. So this is going to be 0, 1, 2, 3, 4, 5, 6. So I'm going to call the function to evaluate the Fibonacci of 6. I'm calling the function, right? So 6 is going in here. So I'm going to have to alter this algorithm a little bit. So 6 goes in, and then as soon as 6 goes in, I'm going to go in here and say, do I know what this value is? And the answer is, does the table have the value of Fibonacci of 6? And the answer is no. So therefore, the Fibonacci, so I'm going to execute this. Fibonacci of 6 is going to be equal to what?
12.
Fibonacci of 5 times the Fibonacci of 4, but I am proceeding to here. Do I have the Fibonacci of 5? No. So I'm going to recurse with 4 and 3, but I'm really proceeding to 4. Do I have the Fibonacci of 4?
No.
No. So I'm going to recurse 3 and 2, but first I'm going to recurse to 3, because I can only recurse one at a time. And my recursion is going to go left first. When I come back, I'll go right. When I come back all the way up here, I'll try to go right. So now I'm going to say, do I have the Fibonacci of 3?
No.
No. So far this algorithm looks ridiculous. So now 3 is going to say, you got to go 2 and 1. Okay. Okay. So what I'm going to do is I'm going to go 2 first. Then I'm going to come back, I'll go 1. So I'll say, do I have the Fibonacci of 2? And the answer is no. So then I'm going to say, well, I'm going to have to go 1, 0. But first I'm going to go 1. So now 1 goes into the function, and if n is equal to 1 or n is equal to 0, then what we're going to do is we're going to say the table, we're going to put into the table, so the table, which is going to be t sub n, is equal to n. So that means we're going to put a 1 here. And we will return the Fibonacci of 1, which is
1.
1. And then we're going to recurse to the right. After we come back, we're going to recurse to the right. This time, we're going to recurse with 0. And the condition, again, is true. Therefore, t sub 0 gets equal to
0.
0. Now, after that, we come back to this node. This node says Fibonacci of 2 is equal to the Fibonacci of the return value of Fibonacci of 1, which is 1, Fibonacci of 0, which is 0. Therefore, this value is equal to
1.
1. And as soon as I compute the value, I will store it into the table. So I'm going to say that's equal to 1. And then, after I do that, I'm going to go back up here. And this one says the Fibonacci of 2 is equal to
1.
1. Plus the Fibonacci of 1. Do I have 1 in the table? Yes, 1. So therefore, this computes the value of Fibonacci of 3, which is
2.
2. Get the idea? So now, after this is 2, this is going to return a 2. It's going to return a 2. Then it's going to say, now I need the Fibonacci of 2. As soon as it goes in, do I have, is it equal to this beginning base case? No. But do I have it in the table? Yes. Fibonacci of 2 is equal to what?
1.
Is equal to 1. So I'm going to return a 1. So the fourth Fibonacci is going to be what?
3.
I will add 2 plus 1, which is 3, and I will record it into the table. And then I'm going to go up. And I'm going to be returning a 3. Here, Then it says, now I need a Fibonacci of 3. Do I have it? Yes. That returns from the table immediately at 2. And 3 plus 2 is equal to? 5. And so now we have 5 plus 3. Am I right? I'm really confused here.
Yes, 5 plus 3.
3 plus 2.
3 plus 2.
3 plus 2 is equal to 5. Okay, so I'm going to return, this is going to return 5. And I'm going to come back to this one, which says, okay, now I need the Fibonacci of 4. Do I have the Fibonacci of 4? Yes, it's in the table. So the first thing you check, is it a base case? No. Do I have it in the table? No. If you don't have it in the table, recurse. If you have it in the table, get it,
And you just return.
and return. And if you don't have it, then compute it recursively and record it. So at that point, I'm going to need the Fibonacci of
4.
4. It's in a table, and Fibonacci of 4 is 3. So therefore, I'm going to add 5 plus 3, and I'm going to record it as 8. So Fibonacci of the 6th Fibonacci number is equal to 8. Okay, so let's find out how much. So you understand? So we did some amount of work. To determine whether the algorithm is exponential or something different than exponential, we have to see what happens as this function is increasing. That's one of the things we can do. And in this case, if we're looking for 7, we'll do all of this, then we'll also do all of this. Really, this is going to get replicated here, right? Of course, so what's going to change? We're going to go from 7, we're going to go to 6, 5, 4, 3, 2, 1. Up here, we're going to do exactly the same amount of work. When I get to 4, I already have it, and then I will return this value equal to 8. By time I have to look at the Fibonacci of 5, it's already in the table, therefore that's going to give me a value of 5, it's going to be 13. How much more work did I have to do? What was the increase? What do you think the increase was?
1.
The increase was, the increase was theta 1.
Increase for what? I'm sorry.
The increase from computing Fibonacci of 6 from scratch versus Fibonacci of 7 from scratch. What does it mean from scratch?
There are no increase in the table.
Yeah.
No interest in the table. From scratch means an empty table, right? So how much more work did I do? Really, the only work I did, I just had one more call. Second call. But the complexity of this one call was theta 1. And the complexity of this call was another 1. Plus the cost of this. So I only increased it by theta 1. So what is that mean that the cost of the algorithm is? If I increase the cost of an algorithm, if I try to do one more higher value, and the algorithm increased by theta 1, what's the complexity of the algorithm?
And what?
Which is correct, which is linear. So it's linear. That's a heck of a lot better than exponential. That's a heck of a lot better. Okay, so exponential, devastatingly bad. Linear, awesome. Okay. So now, let's go back to our LCS. Actually, before I do that, I'm going to try to be nice to the next professor that comes here. So I don't give them a mess like the other person left all his organs in biology here. So now let me give you one more thing before I clear the board completely. Watch this very carefully. So let's draw this again. So we had 0, 1, right? 0, 1. And of course we went to 1, 2, 3, 5, and 8. Notice that we were recursing going this way. But we could have very easily had an iterative algorithm which basically started initializing 0 and 1, just initialize them to 0 and 1, and then go from 3 to n, or whatever it is, take 2 and 1, add them, take 2 and 3, add them. So we could have done it this way, right? So therefore, what we're seeing is that if we draw this table, it doesn't matter how long this table is, we see that the nth entry in the Fibonacci table is dependent upon the n minus first and n minus second. And the n minus first is dependent on n minus second and n minus third, etc., etc., etc. So you can see basically that there's a theta of 1 dependency on 2 cells, which is theta of 1 cell, which means that basically we have an ordering of data. It means that this one, let's call it 0, 1, 2, 2 is dependent on 1 and on 0. That's the ultimate end, right? But these are initial values. So it means that once I have the initial values, I can immediately fill this one in because it's dependent only on the 2 previous ones, which are always, the ones above are always done. So I can remove the recursion completely and just have an iteration. So as I compute the second, the first and 0th are added. As I compute the third, the first and second are added. And so I have what is called a topological order. Topological order is when you can draw dependencies in a table on the values. And this table, in this case, is one-dimensional, but in our example of LCS, our dependency topological ordering will be two-dimensional. But it will still be a topological ordering. If you can draw a topological ordering in a table, that topological ordering will show you the complexity of the algorithm. What you're seeing here is that for each element in the table, that once it's initialized, I only have a theta of 1 operations, which means add, and it's going to be here. Add, 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 add. So the theta of this is n. Okay, questions?
The complexity of the Fibonacci series without the table was 12 when we have calculated previously.
Was what?
Without the table, the Fibonacci series complexity was 12.
2L?
12. 1, 2. 12.
12?
Yes.
I don't know what 12 means. 12 is just a constant. What do we mean complexity? Complexity can't be a constant, can it? Unless it's constant complexity.
Fibonacci of 6.
Oh, just for the value we're looking at. Yeah, yeah. So we were looking at how the numbers are increasing and stuff like that. How, yeah. So the complexity was exponential. It was less than 2 complexity, right? And the reason we know it's less than 2 is because what we found was that the next level took the entire cost of the previous level plus a partial cost of the other level, and so on and so forth. So it's less than 2. They're not quite doubling, but instead of n to the 2, maybe it's n to the 1.6, 1.7. Still exponential. Instead of going like this, it's going to go like this.
So
exponential.
That is exponential, and by using table, it is linear. So
Because of the topological ordering.
Yes.
Yes, absolutely.
so what is the how can we-
Actually, even the recursive algorithm, which was exponential, if we added the table logic into it, would have become linear.
what is the
And I showed you that, right? When we went up one more level through that algorithm, basically, we only did a very small amount of linear addition for each new number.
So how could we get our exact value of the complexity by taking an example of sixth Fibonacci?
Okay, you're still asking for the closed form. I don't have that off the top of my head. I have to think about it.
And out of the Fibonacci series, by using topological order,
Yes.
the closed form I'm asking.
The topological order, it's going to be theta n for Fibonacci.
So if you're looking at the sixth Fibonacci series, so what would be the complexity of sixth Fibonacci series?
Sixth Fibonacci number?
Yeah.
There's no such thing as the complexity of the sixth Fibonacci number. There's only the cost of the sixth Fibonacci number. Complexity is the general cost of an algorithm, not for a specific value, but for the general value. Yeah.
I think what she's trying to say is on with the recurrence tree that we did before, for the sixth Fibonacci number, it took about 12 steps. Like with this with this version, how many steps it would actually take.
Yeah.
Well, with this one, you can see, this is going to be theta 1, put a 0 in here, theta 1, put a 0 in here, put a 1 in here. Then we're going to, here, we're going to simply do one addition. One addition, one addition, one addition, one addition, one addition. So if you call these all operations, the theta, the complexity would be n. Okay, for the tree, what do we say? T of what? T of, do you guys have the t values? I don't have them in front of me. I just computed them. Anybody have the t of 4 and t of 5 and t of 6? Do you have them up there? You had them. Did you write? Who wrote them down? Nobody wrote them down? I don't remember what they were. And I'm not going to recreate them. I know there's a 19, a 12, blah, blah, blah. Look. Okay. T of 6 is going to be equal to t of 5 plus t of 4. So that means it's going to be this plus this. T of 7 is going to be equal to t of 6, which is all of that, plus t of 5. So it's rather than 2 times t of 6, which would be a second power exponential, it's going to be t of 6, t of 5. So it's going to be slightly under 2, because this is going to be slightly under. T of 5 is less than t of 6, but it's still growing exponentially.
So it's like slightly under squaring. Like, yeah.
It's slightly under, not squaring, under exponentiating
Yeah, exponential.
by 2.
Yeah.
So if this for, I think what was t of 6, 19?
12.
12 is equal to 12. So this one was equal to 12 plus whatever was the previous one, 7, I think it was 7, right? So t of 8 is going to be equal to 19 plus 12. T of 9 is going to equal to 31 plus 19. Okay? All right, I don't want to spend too much time on this. I already spent too much time on this. All right, go back to our LCS. You guys are doing everything you can to prevent me from proceeding with LCS, topological order. All right, topological order. Topological order simply means that we can determine, knowing something in the table, we can determine something else in the table. That's the key. Good. Okay. So we're going to assume that precondition is that x and y are global strings indexed from 1 to n and m respectively. And the post is LCS returns the length of the longest common sequence. So we're going to use kind of a table approach here. So we're looking for the LCS of ij, where I is the length of the first string and j is the length of the second string. Initially we have an n coming in and an m coming in. If table ij is empty, if the table is the location is empty, if I is equal to 0 or j is equal to 0, put a 0 in the table. What we're going to do is we're going to create a table which is two-dimensional. And the reason it's two-dimensional is because the first word and the second word are going to go into different dimensions. Okay? So we're going to be looking at intersections of letters where they're matching. Are you with me? And what we're going to do is we're actually going to add an extra row and an extra column, and we're going to put them all with zeros. And I'll tell you what they represent. This whole string is CABXYN. This string is CA. This string is C. Before the C, the whole string is epsilon. So it's an epsilon before the first character. We're going to give it a row. There's also an epsilon before the first character here. We're going to give it a column here. We're going to give that a row, and we're going to put all the rows and columns zeros, because epsilon with any number of characters is going to be 0, LCS. So that's why so what's going to happen is the first row and the first column is going to be populated completely with zeros. And the idea is, how are we going to compute the location ij? How are we going to compute that? So if it is either the first row, which we'll call it the 0th row, or the 0th column, just put a 0. Okay? Else, if the table elements are matching, that means the ith character and the jth character of the two strings is matching. Because we're saying index I from the string x, index j from the string y. If they match, then table sub ij is going to equal to 1 plus the LCS I minus 1, j minus 1. That looks familiar. Because what we did was, when we had two strings that are different strings, and one was px, the other one's py, different string, the p's matched. So what we did was, we took this into the LCS, and then we moved each string forward by 1, and that brought us to the next character, reducing the length of the remaining string by 1, and that's what we're doing here. We're saying here, LCS of I minus 1, j minus 1. Let me show you what that's going to look like. So let's look at a very simple idea here. So there's some characters here. Let's say there's a letter X here, and let's say there's a letter X here. Okay? So now we are very interested, and so this is row I, this is column J. So I and J are coming to the LCS function. Suppose the characters are matching, which means that X, oh, I shouldn't use X because X is a reason for string. So I'm going to say the character, let's say the character is C. C for character. The ith character of the first string matches the jth character of the second string. There's no question that that's going to add 1 to the LCS. So the length of the LCS is going to be 1. But I have to now consider what happened, because before I ever came to this spot, I've already compared this much of the string and this much of the second string. Which means that if I go to location I minus 1, j minus 1, that already had a value in there. Because I'm growing the string, I'm processing the strings forward. So that means that there was an I minus 1, j minus 1 LCS value. Maybe it was 0, maybe it was 1, maybe it was 2. Whatever it was, that was the longest LCS up to that point. Therefore, I'm going to take the value from the table at I minus 1, j minus 1, and I'm going to add 1 to it. So it's going to be 1 plus the table entry at the previous. That's what this is all about. Else means that two characters at indexes I and j do not match. If the elements do not match, then the table entry, so we cannot add anything more. So that happens in a situation, let's look back in here, into that green area. So let's say over here, we do not match. We do not match. That means maybe this character is an A, this character is a D. Or C and D, how about that sound, right? So they're different characters, C and D, for example. So this adds 0 to the LCS. But what we're going to consider is we are going to consider this entire string matching the LCS. So this is basically taking the first string up to and including this mismatched character, and up to the second string, up to but not including this character. Because this D could have been part of the LCS. Can't be here because it wasn't a match, but maybe this D can be part of an LCS here. So we're going to consider the biggest LCS we had using all of the characters of the first string and all but 1, which means we're taking either the P or the Q out. But now we have to consider the possibility that it's possible that this mismatched C might have matched something before here. Maybe there's a C in here. So in that case, we're going to take all of it, including the C here, and we're going to take all of it except for the D here, and we're going, so what's that going to be? That's going to be this value. What's this going to be? The black one. That's going to be this value. So what we're going to do is we're adding 0 because of the mismatch exactly here. But the LCS, if it was so-and-so here and so-and-so there, either of these two, at this point, we will take the maximum value between these two and we'll simply copy it into here. So that means on a mismatch, my ij location, my location I sub j, is dependent on this location. So this is going to be ij. We're going to go ij, I guess. Ij. Let's go ij. Ij. So location ij is going to be dependent upon location ij minus 1. And then here, it's going to be dependent upon location I minus 1, j. That happens on a mismatch. On a match, because we're consuming the matching characters, we cut both strings here, which means our location ij will be dependent on this one, which is I minus 1, j minus 1. So we have a topological ordering, which means that the ij location is dependent upon I minus 1, j minus 1, as well as the one above it, as well as the one to its left. That's the topological ordering. So if I know the values of, if I know, for example, if I filled in the table, if the table is filled in here, and it's filled in here, then I can compute this very simply by comparing the characters and then either choosing the max of these or 1 plus this. And then to do this, I can compute the max of these, or if it's a match, 1 plus this. And so one by one, I'm going to be able to fill in the table. What's the complexity of this topological ordering for each cell? What's the complexity for the topological ordering for each cell? No. Theta 1. Because? For each cell. Because? Only do it through comparisons. To compute ij, I compare the characters, one operation. If it's a match, I simply say 1 plus this. If it's not a match, I say max of this and this. That's theta 1. How many elements in the table? Well, it's nm or mn, right? So therefore, the number of table entries is going to be m times n, right? Now, if we say m is very close to n, they're the same length or proportional to each other, then this would be what? N squared. So therefore, we can say this algorithm is no worse than quadratic in the longer quadratic, right? Which is, so for example, if we have mn, and they're different from each other, very, very different from each other. For example, this one has 10,000 characters. This one has 7 characters. So we're going to have 7, we're going to have 8 rows and 10,001 columns. Okay? Then the bigger value, this will be, let's say, the bigger value, this is the smaller value. If we round this here, we can say this is going to be less than or equal to quadratic in the longer one. But quadratic is a lot better than exponential. Okay, so let's take a look. What's that going to look like? Yeah. That's a good one. This is the recurrence tree. You can see acorn has 5, car has 3. Okay, so that's a nice picture. Let's go to this one. This is the actual topological ordering. So you can see what I'm going to do is I'm going to fill in, this is the first row, which I call row 0. It's going to be all zeros. This is the first column, which is column 0. It's going to be all zeros. As soon as I do that, as soon as I fill in all zeros and all zeros, this will be comparing what?
The top one and the left one and the side one.
So, well, no. But what I'm saying is, remember this is epsilon followed by the first character of the first string, second character of the first string, third character of the first string, etc., etc., etc. This is epsilon, first character of the second string, second character of the second string, third character of the second string. So when I fill in this and this, notice that the topological ordering for this element is prepared. It said there's a 0 and a 0 and a 0. Which characters of the strings am I comparing for this location?
First characters of both the strings.
First character of both the strings. If it's a match, we're going to say it's going to be equal to 1 plus 0. Because I'm consuming both those characters, putting them into a 1, and I'm adding what was the LCS going back 1, but they're epsilon, so it's 0. So I'm going to get 1. Okay, if it's not a match, if the first character is not a match, then what I'm going to do is I'm going to say, what's the maximum between this one and this one? And the answer is 0. So therefore it's going to go to 0. Which means that the LCS from the first character of the first character to the second is 0, which is correct. You can see the zeros, right? That's what I'm talking about, the zeros. And so if I am comparing, for example, the word fair, F-A-R-E, and the word carpet, these values are coming in immediately. They're just zeros, always, because these are the epsilons. Epsilon for carpet, epsilon C-A-R-P-E-T, and epsilon followed by that. So now I'm going to do this one. You see why this is a 0, right? Then this is a 0, why? So this 0 means that the string F and the string CA have 0 LCS. That's what it means. This one says the string F and CAR have 0 LCS. 0 LCS, 0, all zeros. Why? Because F doesn't occur here. But now, what does this 1 mean? This 1 means that FA and CA have an LCS of 1. Well, it just happens because this one is a 1 here. Okay, what does this 2 mean? 2 means that fair and car have an LCS of 2. Fair and car. Do you see? What are the values? Which letters contribute to the 2?
R.
AR. AR. Okay. So therefore, when we get you can see why all this fills in zeros. Now we cannot fill this one until this one is done. So what we're going to do is we're going to go to the right, then we're going to go down. This one we can do because we have our topological ordering. So we're going to have 0 here, 0, and 0. Why? Because A does not match C, R does not match C, E does not match C, and the max of the upper and left neighbors are 0, so it goes to 0. So once I fill in these zeros and these zeros, just happen to be zeros. Are we late? Oh, it's a little bit late. Okay.
I have a test, sorry.
So what's going to happen here, I'm going to get a match here. So now, you see what I have here? Now I'm going to go to this character. So now I'm comparing what with what? I'm comparing A with R. It's not a match. So therefore, I will say, well, so that means FA and CAR, the length of the LCS will be whatever it was with FA and CA, or CAR, I should say here. So this would be FA and CA, and here it's CAR and F. Whatever is bigger. Which one's bigger? This one. So this is still. Because when I add a letter of CA going to CAR, LCS cannot get smaller. So I will always take the bigger of on a mismatch, the bigger of my upper and left neighbors. Which means left neighbor means I'm cutting one character from here, keeping this one. This one means I'm cutting a character from here, keeping that one. And so you can see how I can fill this in. I can fill this in, I can fill this in, I can fill this in. I'm going to fill that in. Now I'm going to go to this character. R matches R. Therefore, I'm going to say it's equal to 1 plus whatever. So car and far is 1 plus whatever was fa and ka. Get it? And that's why this is a 2. And this is 2 because this is not a match, but we already had a 2 here, so we just proceed. And this is a 2 because this is not a match, and we had a 1. What is this 1? Which two strings are defined by this 1 value? Which two strings are defined by this 1 value? FA and Carpat. CRPE and FA is a 1. But now, FAR and E, we don't match, so therefore we already had a 2 for far and carp. So we proceeded. When we go over here, notice that we fill this table in and we compare E against E. That's a match. So there we'll say, okay, let's take out this E from here, go back. Let's take out this E from here, go up here, and we had a 2, so therefore this E makes 3. That's the way we do it. Okay, so this is a topological ordering, also known as a what kind of algorithm? Dynamic algorithm. Table-driven algorithm, dynamic algorithm, topological ordering, all the same thing. So we look at 2 examples today. We look at the Fibonacci, one-dimensional table, where we just have to do the topological ordering with the 2 previous neighbors. And here we have a topological ordering where we are doing 3 previous neighbors. But the reason the complexity of this is n squared is not because the topological ordering for every one element is still theta 1. But now we have n times m elements, and if we round both to be the same, then it's going to be n squared. So the table is 2-dimensional, and for each element we need a linear number of operations. So we're going to say basically the complexity is roughly quadratic. It's big O of quadratic of the max of nm. But it's not big theta. You understand that, right? Does that make sense? So it's big O, but not big theta. Why not big theta? Because it has to be proportional. And the difference between n and m could be substantial.
Why is it quadratic instead of just big O and times m?
Well, of course we can do that. I mean, that would be theta of nm, right?
That's more precise.
And there you have it. Ronaldo has decided it's going to be theta of nm, and that's what we're going to stick at. Okay, we're going to stick with that. So, but what I'm saying is that, so it is theta of nm, but if you want to bring only one variable into the complexity, you can say it's big O of the max of nm. That's still correct. Regardless, so it's quadratic in the length of the longer string. If the shorter string is very short, like 2 or 3 characters, you could almost argue it's linear as a function of the longer string. If the little string is only a length of 3 and the other one has a huge length, and you're looking for the longest common sequences, then you could argue that it behaves more linearly for this special case. So when you have 2 variables, weird things can happen. Okay, sorry I kept you late. See you.